Today's lesson is entitled Inverse Functions, but before we get to the definition of an inverse function, we're first going to remind you what a function is, and then we're going to talk about what a one-to-one function is. So first, the definition of a function. A relation is said to be a function if and only if each x value corresponds to only one y value. Graphically, we used the vertical line test to determine if the graph is a function. And in the lesson that we introduced functions, we talked about how every x can only date one y. Next, I'm going to pass a vertical line from left to right through the graph. At any one vertical line, the graph only touches the vertical line at most one point at every single vertical line as I pass a vertical line through it. Is this relation a function? Yes, it is a function. Okay. Looking at the next graph, as I pass a vertical line through the graph, I notice that my vertical line intersects the graph at more than one point. In fact, in this case, it intersects at 2 points. So right off the bat, I know that this is not a function. This x value has two different y values, and that is not allowed in a function. Every x is going to only match up to one y. In this case, one x is trying to correspond to two different y's, so that's not a function. On the last graph, as I pass a vertical line, at every single vertical line that I can pass through, the graph only touches the vertical line at most one point. So in this last case, we have another function. Next, we'd like to define a one-to-one function. A function is said to be one-to-one. Notice that the relation already has to be a function in order for it to be one-to-one. So we're starting off with a function, and we say it's one-to-one if each y value corresponds to only one x value. Well, and I can also say that f of x or y, because now we know it's a function we can call, instead of y, we can use f of x notation. So every f of x corresponds to only one x. Well, this is very, very similar to the last definition we just talked about. The last definition for a function, every x can only correspond to one y. In a one-to-one function, not only do we have to be a function, so every x has to correspond to only one y, but if it's one-to-one, every y has to have only one x. Graphically, we're going to use the horizontal line test to determine if the functions are one-to-one. These are already all functions. Every single one of these passes the vertical line test, and we can now proceed to determine if these functions, which are already functions, that's a typo there, are one-to-one functions. So I'm going to pass a horizontal line through the graph, and on the first graph I notice that when I pass a horizontal line, it intersects my graph at more than one place. So this function, it is a function, but it is not a one-to-one function. Let's look at the next graph. As I pass a horizontal line through the graph, the horizontal line only intersects the graph at most one point at each horizontal line. Is this a function? Yes, because it passes the vertical line test. Is this a one-to-one function? Yes, it is a one-to-one function because it passes the horizontal line test. Let's look at our last function. We already know it's a function because it passed the vertical line test. In order for it to be one-to-one, I'm going to pass a horizontal line through it, and we see that the horizontal line only intersects the graph at most one point. So then in this case we have, yes, this function is a one-to-one function. This 1-1 means 1, 2, 1. It's just shorthand notation. Sometimes it kind of looks like a broken up H, but it really is 1-1. I just wanted to make that clear. First, I'd like to note that only one-to-one functions can have inverse functions. So I'm going to give you a function, and we're going to start off with a very easy function. I'm just going to give some values here, 1, 2, and 3, 4, 5, and 6. So 1, 2, and 3 are in my domain. 4, 5, and 6 are in my range, and we're going to say 1 is being mapped to 4, 2 is being mapped to 5, and 3 is being mapped to 6. So first of all, is f a function? Well, yes, f is a function because every x value is only corresponding to one y value. None of these x values are repeating and going to a different y value. Secondly, is f one-to-one? In this case, yes. For every y value, or every value in my range, is being mapped to only one x value in my domain. So f is a function, and it is also a one-to-one function. Now we'd like to know what an inverse is. So we have a function, we have a one-to-one function. So I want us to suppose that there exists another function g with the following properties. That the domain of my f function is going to be the same as the range of my g function. Similarly, the range of my f function will be the domain of the g function. So my red values 1, 2, 3, the domain of f, or the input, will now become the output of g. My 4, 5, and 6 values in my range, or output, will now become the values of the domain in g, or my input. And the correspondence stays the same. So for my f function, 1 is being mapped to 4, but in my g function, 4 is being mapped to 1, and so on and so forth. When we have this relationship that the domain and the range are interchanged, we can say that these two functions are inverses. So f and g are inverses. When we looked at g, is g a function? Well, sure, g is still a function because 4 is being mapped to 1, 5 is being mapped to 2, and 6 is being mapped to 3. There are no x values that are trying to be mapped to more than y. Is g one-to-one? Well, all the new y values are only being mapped to one x value, so yes, g is also one-to-one. So what would happen if inside my domain of f I didn't use values? What if I used a variable like x? Well, x would be mapped to, in this case, f of x. And the reason x maps to f of x is because that's the name of the function. So in the inverse, I know that f of x should be mapped to x. Now let us write these mappings in function notation. F of 1 is equal to 4, f of 2 is equal to 5, f of 3 is equal to 6, and f of x, well, is equal to f of x. And that's how we got our f of x value here. Next, let's do the same thing for the g function. G of 4 is equal to 1. Notice that that's the domain and the range are exactly opposite in f and g. Similarly, g of 5 is equal to 2, g of 6 is equal to 3, and this last one here, be very careful. We have g of our domain, and our domain in this case is f of x, g of f of x, and I should be getting out x. Well, what do we have right here? This is a composition of functions. And we already learned how to deal with compositions of functions before. So when we're talking about inverses, we're going to be talking a lot about compositions of functions. This means when I take g of the function f of x, I should get out x every single time. Meaning, if I plug in 1 into f, I get out 4. But then if I take that answer and plug it right back into g, I should be getting out 1, or itself. When I plug in 2 to f, I get out 5. Take that answer, plug it into g. When I plug in 5 to g, I'm getting out 2. I'm getting out itself. I started with 2, I'm ending with 2. Let's jump to the last one. If I plug in x to my function f, I'm getting f of x. When I take that f of x and I plug it into g, I'm getting f of g of x, but I should result in what I began with. Whenever you go through both functions, you should be getting out itself. Let's take a look at this in function composition. If I plug in 1 into my function f, I'm getting out 4. If I compose that with g, I plug 4 in to g and I get 1. Notice that g of f of 1 is equal to 1. I plugged in 1 and I got out 1. Well, let's try this with another number. We'll start with 2. When I plug 2 in, I get out 5. When I plug 5 in, I'm getting out 2. Therefore, g of f of 2 is equal to 2. So whenever f and g are inverses, and when I plug a value into the composed functions, I'm getting out the same value. So if I plug in x to my f function, that gave me out f of x. When I plugged f of x into my g function, I'm getting out x. Therefore, I can write g of f of x is equal to x. And similarly, I could go backwards. If I plugged in, let's say 6, if I plug in 6 to g, I should be getting out 3. Notice I'm putting g first. So I'm plugging in 6, which is a member of my domain of g, and I'm getting out 3 in my range of g. If I turn around and take that answer, 3, and plug it into f, I'm getting out 6. Therefore, we have the same property works forwards and it does work backwards. So therefore, f of g of 6 is equal to 6. I started with a 6 and I'm ending with a 6. When I generalize this, I'm getting f of g of any value x. When I put x into g and then take that answer and plug it into f, I should get itself back if f and g are inverses. So now we've just discussed how we get an inverse. So the definition, if f is a one-to-one function, then g is the inverse of f if f of g of x is equal to x for every x in the domain, and g of f of x equals to x. Both of these statements need to be satisfied in order f to have an inverse, in this case g.